So in this lecture, the goal is to review the vortex sheets that we discussed several class back. Just as an overview, just remember a vortex sheet is nothing else than you have a vortex, but you can have two vortices and four vortices, 8 vortices, and if you have infinite number of vortices, and basically this becomes a sheet, a line of bunch of vortices, and the strength of the vortices is gamma divided by L, or your total vortex circulation is gamma times L. Okay, now if you remember, basically what you're talking about, these are straight lines that there are a bunch of vortices that go across all these points. They go from minus infinite to infinite. This is a sheet. And then they're completely perpendicular to each other. And when we talk about vortex sheet, we are talking about these filaments, if you would, or sheets that have, all these are vortex sheets that go in this direction. And each one of them, as you have infinite number of them, they actually form a nice sheet. And typically we are interested to know what happens to your vortex right here at this point, this location. Okay, so if you remember, we derived this in a couple classes back, where we can have gamma now is a function of S, because there is a source that goes along this line, and then you can have this defined gamma times delta S. The total strength, the total circulation around this vortex sheet is equal to, by this expression, and we derived this couple classes back. And we can write the elemental velocity, the velocity in each one of, at a point P located right here. That velocity is given by this expression here. If you recall, we did that. So we can also find the velocity potential by given by these relationships. And again, this comes from a couple slides back, a couple of lectures back. And then the velocity potential, if I integrate this over this is the expression I will get, and this is the expression we'll use. This is for a sheet that goes 0 to L over some all segment ds. And just know that your vortex velocities is given by this. Okay. Now, one more thing, just if you remember that when you do, we can find the circulation across this with taking the edges out. And the previous slides, in the previous lectures, we learned that this is the equation for that. I'm not going to derive that, so therefore this is equal to this. Now note that your gamma times ds, and so this is equal to this is equal to this, and then there are basically two ways to do this. If it's a thin vortex sheet, right, where when it's thin, your dn is basically equal to 0. It goes to 0. Okay. So another way to look at it is if you compare on both sides, you know this term is immediately 0. Okay, so that's where this comes from. V1 minus V2 has to be 0 because of that. And this term, then this particular term is going to lead to this expression that tells you basically that gamma is equal to the total strength of each one of the vortices is U1 minus U2. Okay? Just remember, this is the Cotta condition that we talked about in the previous lecture. So to understand how this works, let's do a simple example. Let's suppose there's a certain airfoil, okay, and that airfoil looks like this, and then you have a velocity at the top, a velocity at the bottom. Call this U1, call this U2, and the strength of this vortex sheet, so the airfoil can be modeled as a vortex sheet, and then you have those velocities, and the length of that is 0 to 4 meters. So we want to find the strength of the vortex sheet, that is basically gamma. We want to find the circulation, that's capital gamma. We want to find an integral expression to find your velocity potential. Okay, so let's do each one of these cases. The first case is very easy. So we just reviewed this right here. This is u1 minus u2. So this is equal to u1 minus u2. This will be 3s squared minus 2s plus 1, or 3s squared minus 2s minus 1. Okay. The second question is asked, what is the circulation of the vortex? Now, if you remember here, the is given by this expression right here. So we write that there is equal to the integral from 0 to 4 gamma s ds. So that would be 0 to 4, and this is this expression right here. That would be 3s squared minus 2s minus 1 ds. That gives you s cubed minus s squared minus s at 0 to 4. And if you evaluate all that, you find that this is equal to 44 meters squared over second. Okay. The last question, what you asked for is write the integral expression for the velocity potential. Well, the integral potential, and there's part of the description that's not given here. That's given here, sorry. So this goes from 0 to 4, and this is the value of theta. And then if you look at your expression that's given right here, so this is the expression that we'll be using. See, I got theta, I got gamma, I got 2, and 0 to L. So this is the expression. So this will be nothing else than x comma y will be minus 1 over pi integral 0 to 4 sine of, okay, wait, 4. Gamma is nothing else than 3s squared minus 2s minus 1 ds. And then multiplied by theta, that would be sine of pi s over 4. This is given right here, ds. So this is the expression that we are actually looking for. You're not asked to solve it, just to express it. And again, this comes from this expression right here. This is expression that was used here. So for completeness, yes, this came from integral 0 to 4 minus gamma pi theta d of s. So this is just a simple example that wraps up a summary of a nice review of what we did in the past classes.